Hello everyone, welcome to MathSci Ez. Today in our video we are tackling a GCSE physics past paper, particularly this one from 22nd of May 2019. This is a higher tier triple science paper from AQA. So I'll walk you through each question, showing you how to break it down, how to avoid common mistakes and pick up as many marks as possible as we go. So if you are revising for your exam, this is a great way to test your knowledge and to sharpen your exam technique. So ideally what you should do is you need to print the paper. I will put a link to the official website where you can actually print it. And then you need to try each question on your own. So for an example, you go to the first question of your printed copy, right? And just do the first question. So it has question 1 to 1.6, 1.1 to 1.6. So do that question and post this video until that. And then once you're done with that, you can play the video and you can check the answers. So to do this one, ideally for your normal writing, you can use a blue pen. Just use a blue pen for your writing. And you can keep a purple pen for putting your ticks and crosses, and keep another color, probably green maybe, right? And use that for any corrections. So for an example, say you did this first question and you wrote down the equation. If you got this right, no problem, take the purple pen and put a tick. But if you made a mistake and you've written something else which is incorrect, and now you know the correct answer as a result of me talking through this, so take your green pen and write this down. So once you complete the full paper, this is going to be really helpful to you because you have the correct answers, and also you can see how well you did it on your own because it's in green, that's in blue, and then you can see what corrections you've done. So the places where you've corrected yourself are the places where things can go wrong, where you are likely to make some mistakes, and you can avoid it in the future. So that's the idea. So let's quickly get started. So question number 1. Light bulbs are labeled with a power input. What does power input mean? Now, when you're thinking about this question, whenever I see this question, power input, I can think of power is equal to energy divided by time. Also, we can also call it work done over time. Tick one box. The charge transferred per second. No. Charge transferred per second is current, Q over T. So that's not it. The current through the bulb is not power, no. The energy transferred each second, yes. So that's this one, isn't it? Energy per second. So I'm going to go with that. I'm going to put a tick, but just going to check the last one anyway. The potential difference, no, that's the one which you measured in volts. So that's not the answer. The answer is the third one. Write down the equation which links current, potential difference, and power. So the formula here is P is equal to IV. Some people memorize this by thinking about like an ivy leaf, right? Like I don't know if I'm drawing this correctly. So like IV, as in like that, right? P equals IV. A light bulb has a power output of 40. That's my power. The mains potential difference is 230. Calculate the current. Now guys, you can clearly see how I'm doing this. So I'm annotating on the diagrams as I go. So I know the power, I know the voltage, and the current. Obviously, it's the formula that's above. So let's write this down. Write the formula. P is equal to IV. Now I'm going to very carefully substitute. P is 40. I don't know my I, but I know V to be 230. Now what I need to do is, obviously I need to divide both sides by 230. So I can get I on its own. So I can cross them out. Then I know I is equal to, let's use the calculator, 40 divided by 230. I'm getting 0.17391 ... So I've written my long answer here, but in the space where I have to provide my final answer, I'm going to round it to two significant figures. So 0.17 amps is the correct answer. Now, in certain questions, if the question has specifically mentioned give your answer to 1 decimal place or 2 decimal places, so 3 significant figures or whatever, you can stick to that. But in GCSEs, if they have not specified it, usually if it is a decimal, go up to 2 decimal places. But to be on the safe side, you can always write the long answer in the body of the question. So you got the long answer here, then you do the rounding. So the examiner can clearly see that this child actually got this answer and the student has rounded it to 2 decimal places. Right. Table 1 shows information about 3 different light bulbs. Light bulb P, light bulb Q, and light bulb R. Okay. So I can see the total power output in watts, useful power output in watts, and the efficiency of each bulb. Okay. Write down the equation which links efficiency, total power input, and useful power output. This is an easy one. So efficiency is equal to useful power output divided by total power input. This is the correct answer. Now some people I've seen, they try to put 100 here times by 100. That would be percentage efficiency, right? So this question is just asking about efficiency and not percentage efficiency. So you don't need to include 100. You just write useful output divided by total input. Calculate the value of X in the table. Okay. Oh, that's pretty easy because I know the efficiency. I know the total power input. I just need to put it in this formula. So the efficiency is 0.3 is equal to useful power output. Okay, that will be X. And total power input is 9. Now, I need to bring this 9 to this side where it becomes multiplication. So 0.3 multiplied by 9 gives me the value of X. Obviously, X is 2.7 watts. The units is already given here at the end, so you don't get any mark for that. Just put your number in. Right, 1.6. In addition to power input, light bulbs should also be labeled with the rate at which they emit visible light. Okay, so just why? Now, if you think about a light bulb converts electrical energy into electrical energy input into heat energy and light energy. Light and heat both. Input is electrical. So, to really know how good this bulb in how efficient this bulb is, or how good this bulb in converting the electrical energy into the useful energy, which is light for a light bulb, we need to know the rate at which they emit visible light. So let's formulate the answer. I can see this is 2 marks, so they're expecting 2 points. So light bulbs convert electrical energy to light and thermal energy. Now, in addition to the power input, because the power input tells how much energy it uses, but the rate at which they emit visible light, the efficiency will really tell you how good it is as a light bulb. So, the efficiency of the light bulb. Also needs to be considered. Yeah, something to that effect will get you 2 marks. So when you identify that the light bulbs the light bulb converts electrical energy to heat energy, the light and thermal energy, so both parts, right? So that would get you a mark. And the efficiency of the light bulb should be considered before you make a decision, so that's the second mark. So that's question number 1. So at this point you should pause the video and then try and do your second question in your own time, and then just come back and check. But I'm just going to continue the paper, so you know how to do this one now. Question number 2. A student investigated the insulating properties of newspaper. Figure 1 shows the apparatus the student used. Here's a metal can, and you have layers of newspaper around it, hot water inside, a digital thermometer recording the temperature. Okay, the students' results are shown in figure 2. So on the y-axis I have the temperature decrease of the water after 5 minutes in degrees Celsius. Okay, and in the x-axis I can see the number of layers of newspaper. Now the students' data are all recorded here, and you can clearly see when the number of layers of newspaper were less, right, the temperature drop was high. Like when with no newspapers around it, the temperature dropped by 18 degrees in 5 minutes. With more number of layers, the temperature drop really reduced over time. So reduced. So obviously that shows the higher the number of layers of newspaper you have, the greater the insulation. So question number 1. Describe a method the student could have used to obtain the results shown in figure 2. Right. So they have given you the results and we need to devise a method. So what you need to do here is you need to mention about how to get hot water, and you need to mention about the number of layers of newspaper, and we need to talk about how to measure the temperature, and we need to talk about any control variables. The control variables are the things that you need to keep constant to make it fair. So let's start to write this down. So you need to start by using number of layers of newspaper. The student has gone up to 30 something, 32, right? 32. Yeah. Starting from nothing, right? So start from 0. Then the student has done certain number of newspaper. I think it's about 8 layers, and then 16, and so on and so forth, and then 24 here, and then 32, right? So we can use even n for the number of layers of newspaper. So heat water using a kettle. You can also use a Bunsen burner and a beaker, that's fine, using a kettle, and pour a known volume of hot water to the beaker. To the metal can, not beaker. Now, since I mentioned the known volume, let's mention what we use. We can use a measuring cylinder to do this one. Use a measuring cylinder to measure the volume of water. Start with no newspaper layers and increase the number of layers in each step. We can write example 0, 8, 16, 24, 32, etc., which is what apparently this student has done, because the number of layers are around those numbers, so we can include that. You probably don't need to write the numbers if you just change the just to say if you change it, that's fine. Then measure the initial temperature and the final temperature after 5 minutes. Using a digital thermometer. They have used the word digital thermometer, so let's use the same, using a digital thermometer. Then, since we mentioned about the time, we need to mention like what equipment we use to measure that. So you can use a stopwatch to measure the time. Use a stopwatch to accurately measure time. Now, doing it with just once is not enough, obviously. So what we need to do is you need to repeat multiple couple of times to get this right. So let's include that as well. Can record it in a table and calculate the mean. Right, now we have all the data that we need to do this one, and it's worth to mention that we need to use the same initial temperature, so let's include that as well. We mentioned the same volume, which is one of the controls, so use the same initial temperature for each trial. So that would be sufficient to get 6 marks here. So you will get marks for points like heating it with a kettle will get you 1 mark. A known volume of water will carry a mark. Measuring cylinder is an important thing you can say. Start with no newspapers. Change the number of layers. Measure the initial and final temperature after 5 minutes using a digital thermometer. And digital thermometer would get a mark. Using a stopwatch to measure the time. Repeat. And yes, and then the student can use it. We can also just include that calculate the difference. We mentioned about the temperature and the final temperature using a digital thermometer. Let's quickly add that as well. Temperature difference is initial temperature, take away the final temperature. Now, you do not need all of these points to get 6 marks. As long as you got enough points that would correctly explain, you will get marks. So usually these kind of questions, the marks are sort of in bands, in like level 1, level 2, level 3. Now to get a really good answer, if you have given a good design, that would lead to the production of a valid outcome, and all of the major steps are identified and logically sequenced, you should be getting your full marks. That's question number 2, part 1. 2.2. The student could have used a data logger with a temperature probe instead of the digital thermometer. Okay. Figure 3 shows the readings on the digital thermometer and the data logger. So the digital thermometer 67.5 degrees Celsius, data logger, you can see the same value. The data logger records 10 readings per second. The student considered using a temperature probe and a data logger. Explain why it was not necessary to use a temperature probe and data logger for this investigation. Well, you can clearly see that they both measure to the same resolution. Resolution is the smallest reading that you can measure. So imagine if one of them was able to like measure up to 2 decimal places or something, then you would say, okay, that will make it more accurate. But these two, they don't. So we can say both digital thermometer and data logger have the same resolution. I can add within brackets to 1 decimal place. So there is no advantage of using both of them. And it says that the data logger records 10 readings per second. So that seems like a good thing. But in this particular experiment, we are only interested to know what is the starting temperature and what is the end temperature. So although the data logger records all of them, we don't really have a particular advantage in doing that. So let's include that as well. In this experiment, we only need the initial and final temperatures to calculate the change in temperature. So having a data logger and taking 10 readings per second is not going to be any better than having a digital thermometer. So you can see this one is 2 marks. So both of them have the resolution would get you 1 mark. And when you identify that you only need the initial and final temperature to calculate the change in temperature, that will get you the second mark. Question number 3. A scientist investigated how the maximum muscle power of humans varies with age and gender. The scientist asked volunteers to stand on a platform and jump as high as they could. Figure 4 shows a volunteer taking part in this experiment. Here's a platform. An electric timer measured the time that the volunteer was in the air. The muscle power in watts per kilogram is calculated using the following equation. Muscle power equals 9.8 times jump height divided by time. One volunteer has a muscle power of 41 watts per kilogram. Okay. So we know the muscle power. He was in the air for 0.12. Yeah, you just need to really substitute. Let's do that. Muscle power is 41 is equal to 9.8 multiplied by, that's called h for the muscle jump height. And he was in the air for 0.12 seconds. So let's move it to that side. 41 multiplied by 0.12 is equal to 9.8 times h. I'm going to move the 9.8 to the other side where it becomes a division. So let's put it in the calculator. 41 times 0.12 divided by 9.8. It's 0.5020 ... So the question doesn't say to give it to a certain number of decimal places, but I think 2 decimal places is fine. So let's do this one. H is equal to 0.50204 ... And in the answer space, I'm going to write 0.50 meters, half a meter. I wrote it to 2 decimal places. Write down the equation which links kinetic energy, mass and speed. Kinetic energy, mass and speed. So kinetic energy is equal to half mv squared. So you can either indicate it m and v, or you can just write it in words. Kinetic energy is equal to half times mass times speed squared. Either way, you will get marks because these letters are standard letters, but I would just indicate what mass m, speed v and all that. One volunteer had a kinetic energy of 270 joules. So that's kinetic energy, and a speed of 3. Calculate his mass. Now, if you've noticed this, I always, when I read a question, I underline the important bits and I also annotate what they are. Okay, very easy, just submit in the formula. Kinetic energy is equal to half mv squared. Kinetic energy is 270 is equal to half times, don't know the mass, but I know v is 3 squared. Now, I'm going to make m the subject, move the 2 to that side. So 270 multiplied by 2. Now 3 squared is 9. I'm going to make it to the left, bring it to the left hand side where it becomes a division. You can put 3 squared, or you can just put 9. It's the same thing. You can put a calculator, or 9 goes into 270 30 times. That will be 60 kilograms. 60 kilograms is the mass of this person. Next, figure 5 shows the scientist's results. Now, you can see the solid line for male, dashed line for female, and the age of volunteer in years is on the x-axis. Y-axis has the muscle power in watts per kilogram. Now, it's really important to read what the axes are, what are the units and all that, right? Because I've seen many students like just literally just glance over it and go to the next one. That's not a good practice. Please make sure you read it so you understand what you are looking at. Compare the muscle power of males with the muscle power of females. Use data from figure 5 in your answer. Now you can see generally the male muscle power graph is above the female muscle power graph, generally speaking, and the maximum muscle power of the humans, like here, the male, kind of peaks around here, and that is more than the female one. and the maximum muscle powers peak at different times. And also you can see before the age of 10, around here, the male muscle power is less and the female muscle power is more. So you could probably write some of these points to get full marks for a question like this. So let's see what we can. So let's talk about the general trend first. So let me just make it a little small so we can have a look at the graph as well. Here, right. Generally, males have a higher muscle power than females for most of their lives. Now, why do we say most of their lives? Because you can see there's an exception at the beginning, right? So, because this trend starts around the age of 10. So, before the age of 10, females have a higher muscle power than men. Now, at around here, and you can see that's around age 10 years old, you can see the two graphs cross. What does that mean? That means around age 9, 10, males have the same muscle power as females. So let's include that as well. The crossing is, you can say it's 10. Yeah, okay. So around age 10, males and females have the same muscle power. Females have a higher muscle power between the ages. Now, the graph starts around age 5, so between the ages 5 to 9, right? Around there. Now, the next thing we can tell is about the peak muscle power. Now, the peak muscle power for males is here. That's around 25. And for females, it's just around 20 or even 21. Yeah, around 20. Right. So that's the difference. So we can include that. So let's include that one. Males have a peak muscle power at 25 years, whereas females have this around age 20. Right? Now, the next thing you can tell is that generally, especially as you age, the graph kind of follow the same muscle power. So starting from 25 maximum, the male muscle power goes down, and also the same with the female muscle power. So they kind of, especially in the after the peak, they both follow the a similar pattern. So you can say there is a similar pattern for both males and females after the peak. Yeah, I think that's more than enough for 4 marks. You don't really need all of these points to get 4 marks. Again, you can just think of what sort of points would be there in a mark scheme for a question like that. So generally males have a higher muscle power than female, and you can see the solid graph is above the female graph, so that would definitely count as a point, right? And around the age 10 they have the same muscle power. That would be another point because that's where the two graphs overlap. Then females have a higher muscle power between the ages 5 to 9. Now, it's okay to say before the age of 10, but the problem is we don't really have any data for less than 5. So we cannot really talk about what happens before that. So let's do it. It's better to say 5 to 9. Males have a peak muscle power at 25, whereas female value is there. And there's a similar pattern for both around that. So that's like 1, 2, 3, 4, 5 points. You only need 4. That should do the trick, right? That's question number 3.4. You can probably talk about the gradients as well. You can see that the gradients are kind of not the same. So the female one is a little bit gentle, whereas the male muscle power drop is more significant. You can talk about things like that as well. But since we got 5 points for a 4 marker, we'll just go to the next part now. 3.5. The muscle power of each volunteer was measured 5 times. The highest muscle power reading was recorded instead of calculating an average. Suggest one reason why. All right. Now, let's look at the question. The question here, what they really tried to do, right, was to get the maximum muscle power of humans, not about the mean power. So this question is all about maximum muscle power. So the maximum height was measured as an indicator of a maximum muscle power. So the highest muscle power reading was recorded instead of calculating an average because that's the maximum. So let's write this down. The maximum muscle power was investigated and not the mean. So the maximum height reached gives an indication of maximum muscle power. So this is only for 1 mark. Something to this effect should get you the mark. Or you can kind of talk about some other things as well. For an example, if a person was doing this, right? So this person has done it 5 times. A person may not use the maximum effort in their first try. So they might try it once and then they'll feel more comfortable and they might be able to do, utilize it better and give a greater height in the second one. That's one thing. Or you can even kind of say that the performance can get better with practice. The person does the first time and then the second time they might do better. Or the opposite can happen. So if a certain person might use all of his energy, to do it really, do a really good jump the first time, and with tiredness the performance can get worse. So anything like that can also be used to explain this one, but it's just a 1 mark, so something to that effect, or I would go with something that I've written here. Question number 3 is done. Question number 4. Electric cars have motors that are powered by a battery. Diesel cars have engines that are powered by diesel fuel. Table 2 compares one type of electric car with one type of diesel car. Power source, energy density. Now you need to be very careful with this one. This is in megajoules. Mega is 10 to the power of 6 millions. Mass of power in kilogram, mass of power source in kilograms, total mass of car in kilograms, and time to recharge battery in minutes. Okay. The electric car has a range of 400 kilometers with a fully charged battery. Okay. The diesel car has a range of 1120 kilometers with a full tank of diesel. Explain the difference in the time needed to complete a 500 kilometer journey using the electric car compared with the diesel car. Assume both cars travel at the same speed. So if they both travel at the same speed, while it is moving, this creates no time difference. So all of the time difference is due to the recharging. Now obviously you can see the total distance of the journey is more than the full range of an electric car. So the electric car will take a longer time because the battery will need to be recharged along the journey, right? So somewhere along the way they need to just put it to a service station and charge the battery. So let's include that one. The electric car will take longer as the journey is more than the range provided by the battery. So 400 kilometers is less than 500 kilometers. You don't need to include it, but it's good if you do. Now, so it needs, the car needs recharging. Yeah, so I think that's that'll get you the 2 marks. So it says that time to recharge battery or refill the fuel tank. Like, so the battery, it takes 40 minutes to fully recharge. So if they go up to the full charge, it will take 40 minutes more than the diesel car. But you know, you don't need to always go to the full charge. You can do like a partial charge. If that's the case, they will it will take less than 40 minutes obviously, but we can't really give any specific information on that. So the electric car journey will take a longer time, would get you 1 mark. And the next part, so identification that it takes more because it has to be recharged or something to that effect, right? Will get you the mark. Let's go to next question. 4.2. Energy density is the amount of energy stored per kilogram of the energy source. Show why the diesel car has a greater range than the electric car. Use data from table 2. Assume the efficiency of the 2 cars is the same. Okay, it's the same efficiency and you need to include calculations in this one. So energy density, let's see how the energy density can help. Now energy density of a battery is 0.995 megajoules per kilogram, whereas the diesel fuel, it is much larger, it's 45 megajoules per kilogram. So that's what we need to include it. So we can show the total amount of energy stored. So we know the battery, this many megajoules per kilogram, and the mass is 280. If I times these two, That should give you the total amount of energy that is stored in the battery. The diesel fuel has 45 megajoules per kilogram, and the mass of diesel is 51. If I multiply those two, that should give me the total of the total amount of energy. So let's do the calculation. Energy stored in the battery is equal to 0.95 megajoules per kilogram multiplied by 280, which is the mass. Now 0.95 multiplied by 280, that's 266 megajoules. 266 megajoules. Now energy stored in diesel is 45 megajoules per kilogram multiplied by 51 kilograms. That gives me 2295 megajoules. Now, show why the diesel car has a greater range than the electric car. Obviously, the total amount of energy stored in the electric car battery is 266, whereas this one is 2295. So that is significantly more. So you can say 2295 megajoules is more than 266 megajoules. So the diesel car has a greater range. That will get you the 3 marks. Engineers have developed a way of charging electric cars while they are driving along the road. Coils of wire buried under the road transfer energy to the car's battery as the car is passing over the coils. Figure 6 shows a charging lane on a motorway. Okay? Suggests 2 advantages of using this method to charge electric cars compared with plugging them into mains electricity supply. Now, if you can, if the car is being driven on this lane and it is getting charged, now recharging is a continuous process, right? So the cars do not need to stop to recharge. Instead, they can keep on moving and they'll get recharged along the way. So what that means is the journey times will be shorter and the cars will have a greater range. Right, let's put some of these into an answer. This makes recharging a continuous process so cars do not need to stop for recharging. This makes journey times shorter. Now, I kind of include all of them in one point because they are all sort of connected to the same point. For an example, one might say, can I write this make the journey time shorter journey time in the second one? I wouldn't do that because it's kind of linked to the fact that cars are being charged as a continuous process. Now, what else can you, what other points can you think of this one? So another advantage of this would be, right? So now if you look at the mass of the electric car, right? Usually the total mass of the car is a bit higher than 100 kilograms more. in this example than the diesel car. That's mainly because of the mass of the battery. If this is a continuous process, you don't really need that many cells in a car. So what they can do is they can probably make the car a little lighter. So it's a smaller battery which will make the car lighter. On the other hand, that will help to increase the range of the car because it requires less energy when the car is lighter. Right? That will be one point. Let's write this down. Fewer cells are needed in the battery, and it can reduce the mass of the car. Which in turn increase the range. Now also there's another advantage, like when you have it like that, multiple cars can be charged at the same time. Like normally when you're using a plug-in sort of a charger, only one car can be charged at a given time, and once that car is charged and you need to remove the charger, and the next car, the other car has to wait. But here it's kind of linked to the first point. That will actually count as another point. So let me just put an asterisk and write. So multiple cars can be charged simultaneously. Right. So you can have you got 3 points here. So any 2 out of 3 will get you full marks. 4.4. When electric cars are not being driven, energy stored in their batteries could be used to meet sudden peaks in electricity demand. So just how? Right. Normally, what we do is we use the national grid to extract energy into the whatever the equipment we need, appliances we need, including electric cars. But when they are not being driven, like imagine you have a large number of electric cars, they all have stored electrical energy. So when the cars are plugged in, you can use the energy from the batteries to transfer back to the national grid. So that's for 2 marks. So when cars are connected to the national grid, they can transfer energy to the grid. Or alternatively, we can use the energy from car batteries to power the household appliances, the ones that you're in your house. So so that's one thing, or you can mention about energy transfer. So again, in this question, you'll get 1 mark for when cars are connected, and the next thing about transfer of energy to the grid, to give you the second mark. So 2 marks. Question number 5. This is about radioactivity. Polonium 210, so the mass number 210, atomic number 84, is a radioactive isotope that decays by emitting alpha radiation. Complete the decay equation for the polonium 210. Now this is a relatively really easy question. So the mass number should add up the conservation. So 210 take away 4 gives me 206. Atomic number should also add up. 84 take away 2 is 82. So lead 82, 206. explain why contamination of the inside of the human body by a radioactive material that emits alpha radiation is highly dangerous. Now, alpha radiation is highly ionizing. So, which means they can change the DNA, or even they can cause like radiation sickness, poison, all of these things, right? So let's write this down. We know alpha is the most ionizing of all three, alpha, beta, gamma, right? Alpha radiation is highly ionizing. Exposure to alpha can damage DNA and can cause mutations, cancer. Also, high doses can cause organ failure. High doses can cause radiation sickness and organ failure. Now, this is about the inside of a human body. Now, this will keep on happening until the radioactive material is excreted, right? Or when it is, if it has a relatively shorter half-life, so if it kind of comes back down to the background radiation level, right? This will continue until the radioactive material is excreted. Yeah, that will get you 3 marks. So it's highly ionizing. Identification of that will get you 1 mark. It can cause damaged DNA and cancer, radiation sickness, organ failure. Any of these points will get you, and that it will take until this one. So I've marked a couple of points, 1, 2, 3, 4, 5, 6 of them. You don't need all of them. You can, as long as you got 3 valid points, you will get correct marks, right? Next question. A sample of polonium-210 was left for 414 days. Okay. After this time, it had a mass of 1.45 times 10 to the power of negative 4 grams. The half-life of polonium-210 is 138 days. Calculate the initial mass of the sample. Now, in a question like this, we need to find the number of half-lives. How many half-lives left from the beginning? So, number of t-halves is equal to, now 1 half-life is 138. So, 414 divided by 138. So, there you get 3 as the answer. So, we know it spent 3 half-lives to get to 1.45 times 10 to the power of negative 4 grams. So every half-life, the mass keeps on becoming half. So whatever the initial mass has halved 3 times to get to this value. So how do we find the initial mass? You have to double it 3 times. That's the opposite of halving. So the initial mass is 1.45 times 10 to the power of negative 4 multiplied by 2 times 2 times 2. So that's because the initial mass has halved once, twice, 3 times to get to this. So when you know the last one, if you want to find what it was before, the opposite of halving is doubling. So 1.45 times by 2 times 2 times 2 is 8, which is 11.6 times 10 to the power of negative 4. So that is 1.16 times 10 to the power of negative 3 grams. So this was the value that you started. Now, to double check, if you divide 1.16 times 10 to the power of negative 3 by 2, and you divide that answer again by 2, and you divide it again by 2, you will again get 1.45 times 10 to the power of negative 4. So the answer is this. You can leave it in the standard form, or you can write it as 0.00116 grams. Question number 6. Figure 7 shows a person using an electric lawnmower. The lawnmower is connected to the mains electricity supply. What is the frequency of the mains electricity supply in the UK? So we know it's 50 Hertz. So the mains electricity supply changes the direction 50 times per second. The lawnmower has a switch on the side of the handle. Figure 8 shows the circuit diagram for the lawnmower. So you have some motor, power supply, there's a left hand switch and the right hand switch. The motor in the lawnmower can only be turned on when the person using it holds the handle of the lawnmower with both hands. Explain why. Obviously, both switches needs to be closed to have a complete circuit, right? Because if the person just closes the left hand circuit, left hand side, the current can't go because there's a gap. If the person closes this one, then the current can go because it makes a complete circuit. So let's write this down. Both switches need to be closed to make a complete circuit. Then current can flow in the series circuit through the motor. Now for a question like this, both switches need to be closed would get you 1 mark, because the question says the can be only be turned on when the person using it holds the handle of the lawnmower on both sides. So basically when you hold from both sides, what happens is it closed both switches. So identification of that would get you 1 mark, and that it can flow making a complete circuit would get you the 2nd mark. The power out input to the motor is 1.8 kilowatts. The resistance of the motor is 32 ohms. Calculate the current in the motor. Now, the formula here is P is equal to I squared R. So we have 3 equations for power. We used P equals IV earlier. P equals I squared R, again V squared over R. But here I can clearly see they've given me the power, they've given me the resistance, they're asking the current. So obviously it has to be P equals I squared R. Let's substitute the values. Now it's really important to look at the units here, guys. You can see it's 1.8 kilowatts, so that's 1,800 because kilo is 1,000. Okay, so the power is 1800 equals I squared, I don't know, times by 32. So I'm going to divide both sides by 32. Divide by 32, cross, cross. Now that is I squared. So I is the opposite of squaring is square rooting. Square root of 1800 divided by 32. Let's use a calculator. 1800 divided by 32 square root gives us 7.5 amps. So the current in the motor is 7.5 amps. The useful power output from the motor is 1.5 kilowatts. Right. So the question previously said the power input was 1.8. The useful one is 1.5. Calculate the time it takes for the motor to transfer. Okay, so this is the power output and this is the amount of energy. Now, remember the formula, power equals energy divided by time. So power is equal to energy divided by time. 1500, because again, kilowatts, kilo is 1000, 1500 watts is equal to energy is 450,000 divided by T. Cross multiplication, T goes to that side. 450,000 divided by 1500, and you can put it in the calculator. That's 300 seconds. So it takes 300 seconds to transfer that much energy. Done. Question number 7. Figure 9 shows a person sliding down a zip wire. As the person slides down the zip wire, the change in GPE of the person is 1.47. Okay, GPE is 1470 joules. Mass of the person provided, the value of G 9.8. Calculate the change in vertical height. Oh, that's very easy. Gravitational potential energy is equal to mgh. And the gravitational potential energy is 1470 is equal to 60 times 9.8 times by the height. Now I need to get rid of these two to get the height. So I'm going to divide both sides by this. 60 times 9.8. 60 times 9.8. I can cross this out. And on the calculator, 1470 over 60 times 9.8 gives me 2.5 meters. So the height, the change in vertical height of the person is 2.5 meters. As the person moves down the zip wire, her increase in kinetic energy is less than her decrease in gravitational potential energy. Explain why. Now, when the person goes from, say, here to here, if the gravitational potential energy drops by a certain number, let's say 1470, right? The kinetic energy gain could be 1100 or something. So it will be less. The question is, why? So the reason is there is air resistance. So as the person moves, right, work is done against air resistance, or and actually is the air resistance and also the friction between the zip and the pulley. So up here there is some friction between the in this region. So work needs to be done against that as well as air resistance. So the loss of GPE is used to increase kinetic energy and also to do work against air resistance. So eventually it will convert into thermal energy, which means the kinetic energy is not the same as GPE loss. So let's write this down. Work is done against air resistance. You can use the word drag, air resistance, and there is friction between the pulley and the rope. a proportion of energy is used for this, for these, and causes thermal energy transfer. So the kinetic energy is less than GPE. Kinetic energy gained is less than GPE lost. So you'll get a mark for saying work done against air resistance or drag, right? And also you can get another mark for saying the friction part, and yeah, something like that. Different people have different speeds at the end of the zip wire. Explain why. Right. Now, this is one of those questions that I've seen like many students have mentioned, or because they have different masses. Actually, the mass does not have an impact. The reason is, so if you just think about, just forget about the drag situation for a while. So if you think about the loss of GPE is mgh, gain of kinetic energy is half mv squared, and C, the mass gets cancelled out. Really, mass is not the problem here. So what is it then? The main reason here is that the fact that different people have different surface areas. So let's write this down. Different people have different surface areas. So the drag will be different. So if a person has a large surface area, there'll be a greater drag, which means more work is done to overcome those forces. Also, there's another thing, like, like here, this is a zip wire situation. Like, if a person just let go at this point, you'll get that person will be at a certain speed. Imagine if the person presses his or her legs against the wooden structure and get like an extra push, right? So if the initial speed was not 0, right, then it would add to the total energy of the system, isn't it? So because there is no right or wrong way of doing it, so some people might just let go, some people might just push. So also that's the other that could be another reason. Also, the initial speed may not be 0, which would add to the total energy of the system. Right, that's the end of question number 7. Alright, question number 8. A student investigated the thermal conductivity of different metals. This is the method used. Measure the mass of an ice cube. Put the ice cube on a metal block which is at room temperature. Measure the mass of the ice cube after 1 minute. Repeat with other blocks of same mass made from different materials. Okay. Figure 3 shows the students' results. So with aluminium, initial mass of ice cube is 23. They've just got the initial mass, which is, quite similar to each other. Final mass and change in mass of ice cube in grams is provided. Okay, fine. The initial temperature of each ice cube was -50, -15 degrees Celsius. Okay. Why was it important that the initial temperature of each of the ice cubes was the same? Initial temperature was a continuous variable? No. It is a control variable? Yes, you're supposed to have it the same. Let's check the others. Initial temperature was the dependent variable? No, dependent is what you measure. Independent is what you change. You don't change it, you don't measure it, so you just keep it constant to start with. So the answer is initial temperature was a control variable. Which metal had the highest thermal conductivity? So the one with the highest thermal conductivity is the one where there's a greatest change in mass. That means most melting has taken place, because when this melts, it absorbs heat energy of this one, and it travels. Now, if something has a really good conductivity, what happens is it absorbs a lot of heat energy and it transferred away from it really quickly, making a lot of ice to dissolve. So, which one? You can clearly see this is the highest one. 4, that's not 8, 5.93, 5.5 is less than that. So, copper, right? So, which metal? The answer is copper. And the reason it has the greatest change in mass. Yeah, so which means that that's where the most ice is melted. Yeah. Suggest one source of random error in the student's investigation. Right. Now, there are few things you can think of. Like, one is it's very difficult to get exactly the same mass to start with. So the initial mass of the ice cube is slightly different, 25.85, 26 point, although they're pretty close to 25 grams, but it's a little off. That's one thing. And also because of the shape of the ice cube, like the area of the bottom of the ice cube which is in contact with the metal can also change. So that could also be a reason for a random error. So it's one source of random error. Initial mass of ice cubes were slightly different. That's one reason. And the other thing is the surface area of each ice cube touching the metal is not exactly the same. So because that's where the melting takes place mostly, so it matters, right? So the second part, one is enough actually, but the surface area of the face of the ice cube that is in contact with this metal. Right. 8.4. An ice cube has a temperature of negative 15 degrees Celsius. So this is the initial temperature. The total thermal energy needed to raise the temperature of this ice cube to 0 and completely melt the ice cube is 5,848. Now, the specific heat capacity is given, specific latent heat is also given, calculate the mass of the ice cube. That's a good question. So, first, we have this ice at negative 15 degrees Celsius needs to be converted into ice at 0. then that needs to be converted into water at 0 degrees Celsius. So for the first part, there is mc delta theta, E equals mc delta theta. For the second part, it's fusion, so E equals ml. Okay, so the total amount of energy 5848 is equal to mc delta theta for the heating of ice plus ml for the melting process. Okay, now let's plug the numbers in. 5848 is equal to, now I can get m out as a common factor, open brackets. C, specific heat capacity, is 2100 times by change in temperature. Now you can clearly see the ice started at -15 and the ice ended at 0. The difference is just 15. So m is factorized out, C times delta theta, plus m has been taken out, L, specific latent heat of ice, is 334,000. Now I need to make m the subject to get the answer. Obviously I have to divide both sides. So if you want, you can simplify this bit further and then divide, or you can just straight away divide. So let's do the division. So divide both sides by 2100 times 15 add 334,000. 2100 times 15 add 334,000. Now you can clearly see all of that gets completely cancelled out, and I can just find the value of m if I put this in the calculator. So let's do that. Above the line, 5848, and in the denominator I'm entering 2100 multiplied by 15 add 334,000. Okay, and hit the equal button, and I got 0.016 kilograms. 0.016 kilograms is the answer. Right? So that's 8.4. Right, question number 8 is done. Here's the 9th question, guys. Let's have a look. A student measured the width of a solid metal cube using a digital micrometer. Figure 11 shows the micrometer. Okay, so here are the jaws of the micrometer. So you can turn this one until it kind of clicks, and then it will give you the gap between the jaws is recorded here. In this example, it's 18.45 millimeters. The resolution of the micrometer is 0.01 millimeters. That is the smallest reading that you can measure with it. The student could have used a meter rule to measure the width of the cube. Explain how using a meter rule would have affected the accuracy of the student's measurement of width. Right. Now, for a meter rule, the resolution is only 1 millimeter. So to understand it, think about a meter rule. The centimeters values are marked, and each centimeter is divided into 10 smaller units, and each one is a millimeter. You can't really go below that, right? So obviously that will be less accurate. So let's write this down. A meter rule has a low resolution of 1 millimeters. Now this one is 0.01 millimeters is smaller than that. So using a micrometer gives a more accurate value. So the question is, explain how a meter rule will have affected the accuracy of the student's measurement of width. So a meter rule has a low resolution, that would get you 1 mark. And then the using a micrometer gives a more accurate value, it gives you the 2nd mark. You can also use the converse argument and say using a meter rule would give a less accurate value. They both mean the same thing. So that would get you the 2nd mark. So 2 marks. The mass of the metal cube was measured using a top pan balance. Okay. The balance had a 0 error. Okay. When it has a 0 error, that means when there is no mass on the top pan balance, it shows a reading. That's not 0. Because when there's no mass, it should read 0. But when there's a 0 error, it already shows something without some reading, without having it. Explain how the 0 error may be corrected after readings had been taken from the balance. So that's actually pretty easy. So all you need to do is you need to record the value of the 0 error without any object, and at the end you can record it. Like simply think when you have the here's the top pan balance. When there's nothing on it, it shows 0.2 grams. So you put the object and now it shows say 3.6 grams. Oh, what that really means is because it started from 0.2, this is really only 3.4 grams because that initial 0.2 you should take away, right? So let's write this down. That's how to fix the just how to compensate for the 0 error, right? So the first thing is record the value of the 0 error without any object on the balance. And then what you need to do is subtract the value of the 0 error from the reading. Now, sometimes these top pan balances, right, because you can tell it, sometimes it might have a negative value. Say, if it reads negative 0.2, then that needs to be added, right? So normally if it is a positive value, you have to take away. If it is a negative value, you need to add, okay? Add or subtract the 0 error from the reading to get the correct mass. Done. The width of the cube was 18.45 millimeters. The density of the cube was 8,000. Calculate the mass of the cube. Okay. So density is mass over volume. Mass is density multiplied by volume. Now the density is 8 times 10 to the power of 3 or 8,000 multiplied by the volume. Now this is a cube, so you have a length, width and height. You just need to multiply them. However, you need to be really careful here. This density is in kilograms per cubic meter, but this is in millimeters. So you have to convert millimeters to meters first. So 18.45 divided by, there are 1000 millimeters in a meter, 1000, and then you need to cube it. Why cube it? Because length times width times height. So let's put this in my calculator. 8,000 multiplied, open brackets, fraction button, 18.45 at the top, 1000 at the bottom, close the bracket and cube it. And I hit the equal button. I'm getting the mass as 0.05024 ... So I wrote the long answer here. Now I'm going to round it to 2 decimal places. Actually, because this goes up. Okay, let's leave it as 0.0502 kilograms. That's question 9.3. Okay, let's go to the next question. Question number 10. Figure 12 shows a student after rubbing a balloon on his hair. The balloon and hair have become charged. Describe the force that acts on the student hair in figure 12. And you can say, so you need to describe the force, not state what it is. Now this is definitely an electrostatic force, right? And act on the student's hair. So you can see students' hair are attracted towards this because these are oppositely charged. So you can say, describe the force. Electrostatic attraction force between the hair and the balloon. Right, so usually the 2 marks allocated here. Once you identify this is an electrostatic force, that will get you 1 mark, and this is an attraction, will give you the 2nd mark. You can also mention, because it's a description, describe the force, right? And this is a non-contact force because they don't need to be in touch, because these are field forces. Right? Field forces are, they can act at a distance. So you can, within brackets, say this is a non-contact force. Now, for this question, some students thought about the forces between the strands of hair and said that they are repulsive, and that's also a correct one. But yeah, this question is probably expecting the first one. But also, if you say there are electrostatic repulsive force between hair of the students because they have the same charge, which make them stand on their ends, so that's also fine. 10.2. An earthed conductor was brought near the charged student. A spark jumped between the conductor and the student. The potential difference between the conductor and the student was 2.5 kilovolts, which is 2500 volts. The energy transferred by the spark was 0.0050 joules. Calculate the charge transferred. So remember, V is equal to E over Q. Voltage is equal to energy divided by charge, or work done over charge. So the charge is energy divided by voltage. So the energy is 0.0050 divided by 2500. So let's put it in the calculator. 0.005 divided by 2500, which gives me 2 times 10 to the power of negative 6 coulombs. 2 times 10 to the power of negative 6 coulombs. Or you can write 0.5 zeros and a 2. 0.00002 coulombs. That's the same thing. A defibrillator can transfer a charge to regulate a person's heartbeat. Figure 13 shows a defibrillator. When the defibrillator is in use, the potential difference of 4800 volts is applied across a person's chest. A charge of 0.16 coulombs, that's the Q, passes through the person's chest in 4 milliseconds. This lowercase m stands for milli, so that's 4 times 10 to the power of negative 3. calculate the resistance of the person's chest. Now, let's see what we can do to find the resistance. Now, I know the charge and time. Oh, that means I can easily work out the current, because remember the first formula you learn in electricity is I is equal to Q over T. So Q is 0.16 over 4 times 10 to the power of negative 3. Let's put this in the calculator. 0.16 divided by 4 times 10 to the power of negative 3. And the answer is 40 amps. Okay. So we know the current is 40 amps. To find the resistance, V is equal to IR. R is equal to V divided by I. And V is 4800 divided by 40. And that gives us directly 48 over 4 is 12. 120 ohms. 120 ohms is the answer. Question number 11. Figure 14 shows a Bunsen burner heating some water in a beaker. Eventually, the water changes into steam. Explain how the internal energy of the water changes as it is heated from 20 to 25 degrees Celsius. Now, as the temperature increases, what happens is the water particles gain kinetic energy, right? Which means the internal energy gets higher. So let's explain this one. The mean kinetic energy of water molecules increases with temperature. So what that means is the internal energy will also increase, right? So the internal energy increases as temperature rises from 20 to 25 degrees Celsius. So the mean kinetic energy of water molecules would get you 1 mark, and the internal energy increases would get you the second mark. How is the particle model used to explain the difference in density between a liquid and a gas? Particles in a gas have less kinetic energy than particles in a liquid. No. Gas particles are usually, they are faster, so they are moving faster. There are more spaces between them, so they have more kinetic energy. Particles in a gas have more potential energy than particles in a liquid, right? Difference in density. Yeah, that could be the answer. Let's just let's think this could be the answer and check the other ones just in case. Particles in a liquid are further apart than particles in a gas. No, in gases, particles are furthest, so that's not the answer. Particles in a liquid are larger than particles in a gas. No, particles are the same, right? So all the particles are the same. They're just at different distances if it is the same material. So particles in a gas have more potential energy than particles in a liquid is the correct explanation. Yeah, that's the one. Okay, the last part. A student measured the mass of boiling water that was turned into steam in 5 minutes. Okay, so we know the time is 5 minutes. Now for these calculations, you need this in seconds. So 1 minute is 60 seconds. So I know that is 300 seconds. So I'm just going to quickly mark it here. Explain how the student could use this information to estimate the power output of the Bunsen burner in watts. Oh, okay. Right. Now, the water is already boiling. A student measured the mass of boiling water that was turned into steam in 5 minutes. Now, this is E is equal to mLV, which is specific latent heat of vaporization. So, if the student can measure the mass and you multiply that one by specific latent heat of vaporization of water, that will give you the total amount of energy. Oh, it's easy to get the power because power equals energy over time, right? So let's do this one. Power is equal to energy divided by time. So energy provided by the Bunsen burner is equal to the energy used by water to convert liquid to gas. This is an assumption, assuming no energy is lost to the surrounding. So we can calculate this one by E is equal to m times L. And time taken is 300 seconds. So all the students needs to do is plug it in the first formula, energy ml divided by time. So usually for a question like that, identification of power equals energy over time would get you a mark. Energy conversion will get you a mark. And E is equal to ml will get you another mark. Then the power output of the Bunsen burner being equal to that would get you the other mark. Okay, so that's basically the end of the paper. It took us some time to complete the paper, but we've discussed every single question now. Now, you should have marked your answers according to what we did here. And then what you need to do is you can make a list of topics that you need to work on based on this paper. So you've done the paper. So see in what questions you lost marks and then see what is that topic. So for an example, if you lost marks in the radioactivity question, you know you need to revise your radioactivity before your next paper. So please make sure you do that, and then we will continue this with another paper. All right, thank you.